Lecture 5. In this lecture, we will introduce a very important random variable called geometric random variable, and it is usually denoted as GEO with a parameter P. We will also analyze a problem called branching process problem. But before that, we will give a tool which is about summing a lot of terms, infinite number of terms, and then we will give a corresponding concept called conditional expectation. So let's start. So first of all, in the following, we have two infinite sums. The first one is 1 plus r squared plus r cubed, and so on and so forth. And the other one is 1 plus 2 times r plus 3 times r squared plus 4 times r cubed, and so on and so forth. Here, we assume that r is a certain real number, a fixed real number, and the absolute value of r is strictly less than 1. For the first formula, we claim that the result will be equal to 1 divided by the term 1 minus r. And for the second one, the sum will be equal to 1 divided by the square of 1 minus r. So let's see why this is true. For the first formula, let me copy it again here, 1 plus r squared, and so on and so forth. And we denote this sum that we want to find as the term z. When z is equal to this one, we can multiply z by r so that we get r times z. So r times z will be equal to r plus r squared plus r cubed. So for convenience, I just move the term a little bit around so that it looks like this one, aligned. Now, we can use the first equation minus the second equation so that on the left-hand side, we get z minus r times z. And on the right-hand side, we will see that all the terms that is related to r, they are going to be cancelled so that there is only one term left, which is 1. So we get z minus r times z is equal to 1. So after rearrangement, we will get z, which is equal to 1 divided by 1 minus r. And z is exactly the sum that we want to find, so that we have now just proven the first formula. Now to get the second formula, it is also easy. Let's take a look of the first formula and the second formula. They are actually related. If we perform differentiation of the first formula with respect to r, so we differentiate this one, 1 becomes 0, r becomes 1, r squared becomes 2r, r cubed becomes 3r squared, and so on and so forth, then we see that the left-hand side of the second formula can be derived from differentiating the left-hand side of the first formula. So in that case, if we differentiate 1 over 1 minus r, then we should get the result. And then this is the result for differentiating 1 divided by 1 minus r. So again, we can easily get the second formula. Okay, so these are two formulas that we will use frequently when we analyze the geometric random variable that we will introduce soon. Okay, now we will talk about a new concept called conditional expectation. It is actually a very simple concept. So let's see. Suppose that we have a random variable x and a certain event, let's call it f. The conditional expectation, we have the notation expected of x given f, is defined by the summation of I multiplied by the probability that x is equal to I given f. So what does it mean? So normally, expectation of x or expected value of x is what is the average of x that we expect in the long run. Now we have a new event f that is given for free. Then when we are having this new event, this should change our view of the probability of each thing to occur. So it will change the probability of x is equal to 1, probability of x is equal to 2, and so on and so forth. So in that sense, when f, a certain event, is given, then we should expect a different thing about the expectation of x. It is because the probability changes. So in particular, original probability of x is equal to I will be now probability of x is equal to I given f. So in that case, after the change in this probability, we will have a new expectation. And this new expectation is denoted by expected of x given f. So this is just a very, very simple idea. Original expectation, we have no assumption of what things to happen. So we have a certain view of what is the probability of things to happen. But now, given the knowledge that f happens, then we will change our view. And correspondingly, we will change the expectation. Now, if we are okay with this one, then immediately we can also get the expectation of x given f to be written as an alternative sum. This is summation of all the little omega as the outcomes. The chance that omega, the value of omega when it is applied on x, okay, but this time we multiply with the probability that omega occurs given f. So we change the probability, but then the values we do not change, okay. So here, let us see an example. Suppose that we are rolling a fair die 2 times. We let x1 to be the result of the first roll, and then we let big X to be the sum of the 2 results. We want to find out what is the expected value of x given x1 is equal to 1. And also, let's also try another one. What is the expected value of x, but this time given x1 is equal to 2? Now, in the first case, when x1 is equal to 1, then what does that mean? We now know that the first row has to be 1, while the second row could be equal to 1, 2, 3, 4, 5, 6 with equal probability. So that means that the total sum could be equal to 1 plus 1, or 1 plus 2, or 1 plus 3 up to 1 plus 6. And then each of them has the same chance of occurring. So that means that to compute expected of x under the knowledge that x1 is equal to 1, we should have 1 over 6 chance to be equal to 2, plus 1 over 6 chance to be equal to 3, plus 1 over 6 chance to be equal to 4, and so on and so forth, up to 1 over 6 chance to be equal to 7. So after getting this, so we will get the value of 4.5, if my calculation is correct. So you can also verify it by yourself. Now similarly, if we are given a different piece of information, suppose that x1 is now known to be equal to 2 instead, then we will have the probability of having x to be equal to, so what is the possible values of the sum? The possible values of the sum will be equal to 3, or 4, or 5, or 6, or 7, or 8, or 9. Yes, so, no 9. So it is ranging from 2 plus 1, 2 plus 2, up to 2 plus 6. And then each of them would have equal probability of occurring. So in that case, the expected value of x under this condition, x1 is equal to 2, will be equal to 5.5. So this is the meaning of conditional expectation. Now we have linearity of expectation, and similarly, we have linearity of conditional expectation. So this is like this: the summation of the linear combination of xi given a piece of information f will be equal to the linear combination of the expected value of xi, but then for each of these expected value, it is a conditional expectation given the value, given the event that f occurs. Okay, the proof of this one is exactly the same as we prove linearity of expectation. So I will leave this for you as an exercise. Okay, so let's take a look of an example. Okay, So this is actually the same example as before. This time, let me recall it. So we are going to roll a fair die 2 times. We let x1 to be the result of the first row. And here, for simplicity, we also define x2 to be the result of the second row. Again, x is the sum of the two results. So we want to find out what is expected of x given that x1 is equal to 1. Now recall that the big X here can actually be written as x1 plus x2. So this is actually expected of x1 plus x2 given x1 is equal to 1. So by linearity of expectation, we get expected of x1 given x1 is equal to 1 plus expected of x2 given x1 is equal to 1. Now for the first one, if I tell you that the first row is equal to 1, what is the expected value of x1? So of course it will be 1 because all the time it has to be 1. It is equal to 1 for 100%, so it is equal to 1. Now for the second value, what is the expected value of x2 given x1 is equal to 1? Now we see that x2 is about the second row and x1 is about the first row, so these two are obviously independent. So expected of x2 given x1 is equal to 1 is simply expected of x2 because they are independent of each other. So in that case, expected of x2 given x1 is equal to 1 is equal to 3.5. And summing 1 and 3.5, we get 4.5. So again, we get the same result as we have derived before, but this time we are using linearity of conditional expectation. For conditional expectation, we have also a very important result. Let us call it conditional expectation formula. We will make use of this one frequently in this class. So suppose that we have a certain events E1, E2 up to EK, and they are forming a partition of the sample space. So what does that mean? So it means that all these events, they are disjoint. They don't have any common outcomes. But on the other hand, all the outcomes of these events will cover the whole sample space. Now, for a random variable x, expected of x is going to be equal to, always equal to, the weighted sum of the expected of x given ej. So what is the corresponding weighted value? So the chance, so expected of x given ej is going to be weighted by the chance that ej happens. So actually, this corresponds to something that happens in real life. Suppose that I want to find out what is the average height of all the students in two classes, Class A and Class B. Now, what I know is, I know the average height of the student in Class A, and I also know the average height of the student in Class B. So how can we compute the average height of all the students? So we need one more piece of information. If you can tell me how many students are there in Class A and how many students are there in Class B, then I would be able to compute what is the average height of all the students. So the average height of all the students will be equal to the ratio, okay, of or the proportion of the students in Class A. So Class A divided by Class A plus Class B multiplied with the average height of students in Class A plus the proportion of students of Class B multiplied by the average height of the students in Class B. So in that case, we get the average height of all the students. And this is an example. This is one of the particular example of the use of conditional expectation formula. And how do we prove it? Okay, the proof is like this. Okay, so we start with the term on the right-hand side. This is the term on the right-hand side. We hope to show that it is equal to expected of x. Now what we can do here is we are going to replace this expected of x given ej by the definition of this conditional expectation. So I just copy this from the previous slides. And now we have summation j, summation I, because we are summing all the possible pairs or cases for ij. So these two summations, I can just switch the order. So I make it into summation I, summation j instead. And also, as we see, this probability of x equal to I given ej multiplied by probability of ej can be simplified. They can be combined into this term, probability of xi intersects ej. So far so good. So this is how we derive from the second formula to the third one. Now this I term is independent of j. So when we summation of j of I something, this I is kind of a constant with respect to j. So I can move the I outside. So we get summation I of I, and then the summation of the remaining part. And this remaining part, we are summing probability of x is equal to I intersect all different j's, all different ej's. So this is actually the law of total probability. This summation term actually is exactly the same as probability of x is equal to I. So now, after a few simplifications, we get expected. So this summation formula on the right hand side is the same as summation of I times probability of x is equal to I. And this is exactly expected of x. So we get the conditional expectation formula proven. Okay, so this is the end of part 1 of this lecture. Thank you.